Welcome to another unit in the ISM exercise set Business Mathematics. This time with a unit on Lagrange multipliers. Let's have a look at the exercise. Here we have calculate all possible extrema of the function f of xy under the constraint g of xy equal to 0. With a comment, a proof that they are valid extrema is not required. Then we have for f x squared times exponential function of y plus 1, and for the constraint g being x squared plus y squared minus 1. Well, whenever we read something about a constraint that needs to be observed while another function should be optimized, then this calls for the so-called Lagrange multiplier approach. In this context, we first need the so-called Lagrange function. The Lagrange function can easily be constructed by simply taking, and that's the first part here, the original function f, that's this part, and then for each constraint we add a Lagrange multiplier lambda, which is this one here, and in the brackets we put the corresponding function describing our constraint. So here there's just one constraint, so we just need one lambda. If we were to have like 2 or 3 or more constraints, we would have like lambda 1, lambda 2, lambda 3, and so forth. So it's just f plus Lagrange multiplier lambda times function g. Once we have this Lagrange function, that's basically it about the Lagrange approach, because then we simply calculate possible extrema of this Lagrange function. So here, from this point onwards, it's basically the same as working with unconstrained problems. Well, with unconstrained problems, the first thing we would do is calculate first derivatives, set those equal to 0, and solve the corresponding system of equations. Well, let's do this. So let's start with the derivatives. Here, if we take the derivative for x, well, 1 does not contain an x, so we can skip this. Here, the exponential function of y also does not contain the variable x. So this acts as a constant, and we can simply copy this down here. So we only need the derivative of x squared. Well, the derivative of x squared is simply 2x. So we pull the 2 in front and reduce the exponent by 1, giving us this one. Then we have lambda times that part. Well, only the x squared is of interest here. So we need to get the derivative of lambda times x squared. Well, lambda, constant in this context, parameter. Then again, only the derivative of x squared is required, giving us here 2x times lambda. Then we do the same thing for y. For y, again, the plus 1 is dropped. There's no y there. And here the y is only in the exponential function. So the x squared is just copied down here. The derivative of the exponential function remains the exponential function, so we can also copy this part down here. So no changes in this part. Then we have back here lambda times the brackets. Well, only the y squared is of interest, so we have lambda times y squared. The derivative is 2y times lambda. Well, if we look closely, what we can see here, the first part, this here, is nothing else than the derivative of the function f, this one here, that one here. The second part is the derivative of the function g for the corresponding variable times the Lagrange multiplier. Well, so far so good. That's the first two, and then we only need the third one, the derivative for the parameter lambda. Well, that's just the only place where lambda exists. All these parts don't contain a lambda, So we can simply copy the expression in parentheses down here. Meaning the third derivative for the corresponding Lagrange multiplier always is the respective function g, the respective constraint. Well, that's already all there is for the first derivative. So just take them, set them equal to 0, giving us these three equations. Those we need, or this system we need to solve for x, y, and well, potentially lambda. So we'll just copy them here to have a bit more space. If we start, well, we can take a close look at the first equation, seeing in this context that we have an x here, an x here. So we could simplify this equation by dividing this whole equation by 2x. Okay, if we do this, we first need to assure that x does not become 0. So we need to do a case division. We need to first consider the case x being equal to 0, and then the second case x being unequal from 0. Okay, let's start with the case what happens if x is 0. Well, in this case, the first equation simply reads 0 being equal to 0, because this is 0, this is 0. So first one is uninteresting. The second one, well, we have a 0 here, so this becomes 0, leaving us only with this part back here. If we insert 0 for the x in the third equation, we get this. Since here we only have one variable, we can solve this for y. So we bring the 1 to the right side. We take the square root, giving us a solution of plus minus 1 for y. Now you might be a bit skeptical. If you insert this here, you get plus minus 2 lambda being equal to 0. Well, since lambda can take any values, can take value of 0 or any other value, here this simply means this solution would result in a lambda being 0. So this is a valid solution, 0 plus minus 1. That's our first pair of solutions. Now we consider the second case. What if x is different from 0? Well, in this case, I can divide by 2x, meaning I get a simplified version of the first constraint of just x of y plus lambda. Well, then I can just bring the x of y to the right side or left side, making it look like this. So one side the lambda, the other side what remains. And I'm doing it like this because then I can use this first equation to replace lambda in my second one. That's actually a next step. I take this formula for lambda and I replace lambda in my second equation, giving me this result. So what can I do here? Well, I see the first term has an exponential function. The second term has an exponential function. So I can divide the whole equation by exp of y. Well, in this context, first the question, are we actually allowed to do this? As I said above, we can only divide by anything containing a variable if it's not 0. Well, here we don't need this distinction or this split into two cases, because the exponential function is always positive. So it will never become 0. So we can simply divide by the exponential function of y. Doing this on the left, or with the left term, with the right term, leaves us with x squared minus 2y equal to 0. So we bring the 2y to the right side, giving us this simplified equation or new equation 4. Well, here we have x squared. In the third, we have x squared. So we can simply plug this into the third equation giving us then 2y plus y squared minus 1 equal to 0. That's a typical quadratic equation. So we can either use the PQ formula, the midnight formula, or quadratic extension to get our solution. This here assumes we take quadratic expansion. Well, whatever you use, you will get two solutions to this. The first one being 0.4142, the second one being minus 2.4142. So those are the y coordinates. Now we need to check what the corresponding x coordinates would be. So I simply copy those two results for y, and I copy the corresponding equation 4, because here, if we insert y, we can directly get x. Well, if we insert the first y, we will get plus minus 0.91202. So this y value gives us those two x values. So we have two additional solutions here. If, however, we insert the second y value, we'll get x2 squared is equal to minus 4.8284. Since this is negative and the square can never become negative, not in real numbers, this means this equation is not solvable, so we do not get any solution for the y2. So we only have the two solutions from the slide before, and we have the two solutions here, giving us a total of 4 solutions to this problem. Well, that's then everything there is to this exercise on Lagrange multipliers. So I say goodbye until next time, and if you're interested in more exercises or other additional stuff on math, just check out the corresponding playlist. I'll say goodbye. Well, see you next time.